Well, I think we'll start. We have quite a bit of time for this session today. So we have 4 presenters in 1.5 hours, which I think is very nice. This is one of the sessions where we actually have a good ground for discussion. And I think, especially when it comes to resource recovery, there's a lot of interest, and you sometimes have experts. What I would like is, I would like to ask our audience to answer me 2 questions, would be great. So my first question would be, why did you pick this session? So why did you not go to focus on Vietnam or on-site? What's your particular interest in this session? And maybe to also give the presenters some guidance, I would like to ask you what you expect from the session. So what's your expectation? What would you like to hear? Just something around that. So if I could get maybe 3 volunteers to give me an answer to that, that would be great.
Good morning. Yeah, I came here because Karthik told me to come. No, I'm really interested in seeing what the progress is on converting fecal material to value-added products. And particularly interested in how they're thinking about separations processes afterwards. That's the issue when you're trying to think of fatty acids and alcohols and those kinds of things.
Excellent, thanks.
Hi, good morning. I'm Chris from Zimbabwe. I'm interested in this session because I'm also working on such kind of projects, like using the anaerobic technology to reduce sludge for energy company and nutritional value of the sludge. So I've seen from the lab how they follow what they've done from the lab and actually adapt to upscaling and also the characters that you can also improve this energy company.
Excellent, thanks. That's volunteer, great.
Yeah, I'm interested in new technologies and how it can be adapted. My request, maybe the request to the presenters, I would like to know if their project is research scale, or it's a pilot study, or is it already established, and looking at what are the capex and risks, just to understand how feasibility is actually to
Yeah, great, thanks a lot. We could take one more. There's someone who really would like to say why he's here. Okay, there you go. So I think, yeah, that's very nice, and I think we can already see there's a wide interest in these different topics, and I think there was one guidance question a little bit for the presenters, which might be related maybe more of a business background, but really for implementation. I think that's very important. Where are we going with this? And maybe I can briefly tell you why I'm here. So my name is Lars, I'm working for Sunday Earmark, and for the last 2 years I've been working on a project that looked into feasibility studies of business models for resource recovery. There was resource recovery of nutrients, energy, and water, but not only from fecal sludge. And I think one of the main things we have seen as our technical analysis, which is what I was responsible for, that there are not so many technologies yet, especially in fecal sludge management, where we can really recover resources and have a valuable reuse. So as guidance for the presenters, talk a little bit about, is it scale, is it research, OPEX, and these type of topics. So with this, I see the room is filling up, and I would like to introduce our first presenter. We have got, Karthik Chandra from Columbia University, USA. Karthik is an associate professor of Earth and Environmental Engineering, and he's working in the water, energy, food, and sanitation axis. So please give the floor.
Good morning, everyone. Is this good? Can you hear me? Okay. All right. So today I'm going going to focus on predominantly, given the time, I'm going to predominantly focus on one of these two aspects here, and that's the conversion of fecal sludge into valuable products, perhaps a bit higher on the value chain than some of the more conventional end products that we've been looking at mostly at this conference, and that's biogas. And I'd like to acknowledge my co-author, Shashwat, is doing his PhD. His overall focus was, again, resource recovery, of which this is but one option. And so I don't need to spend too much time on this, given the focus of this conference, given the expertise of the audience here. In any case, the lack of adequate sanitation continues to be a challenge, and this is a far more complex situation. It's not because people, we can't make generalities basically. It's not because there's no money, there's no energy, there are no resources. I think it's an intermingling of several factors here. And so I'm sure all of you have seen schematics like this. This is particularly telling. This is a large plume of fecal sludge that is coming out into the Atlantic Ocean. It's ironic because across the highway from where this fecal sludge plume is, there's also a big plant which is sitting, and there's no fecal sludge going there. It's just sitting empty, and then you have the fecal sludge plume that's quite expensive. And essentially, one of the challenges is the lack of available energy, the lack of available resources to handle sanitation. It's not just money. It's just access to energy. Energy might be available, capital might be available, but it may be a little far away, and that sometimes acts as a barrier. And so the question that we are trying to ask here is it possible to link improved environmental health, improved sanitation, to higher value chain commodity chemicals and biofuels? And again, the point is we're not trying to compete with oil refineries, we're not trying to compete with chemical refineries, we are trying to render the whole enterprise of sanitation resource neutral or resource positive to drive sanitation locally. So having said that, the focus here is our chemicals and biofuels. The principal biofuel that we are interested to start with is biodiesel. So let's start with what biodiesel is. Essentially, biodiesel is formed by the combination of fat, triglycerides, and methanol, which is a very simple chemical molecule containing just one carbon. That's biodiesel, basically. And this is what we are trying to make from fecal sludge, from the organics fecal sludge. Now, what are lipids? And so biodiesel is formed by the combination of lipids, fat, triglycerides, and methanol. What are lipids? Lipids are essentially long-chain acids which have a glycerol vacuum. When you go to a doctor, this is what some of us get on the chart. And this is what we focused on. There are lipids in fecal material as well. You know, we as any cell essentially takes some simple carbon and makes complex carbon. One of the forms of complex carbon comes under the umbrella of lipids. And what is the lipid content? The question to ask is what the lipid content of fecal material or feces could be. Again, if you look at a healthy individual on a dry mass basis, the lipid content could be about 6%, 7%. And this you can read from medical journals, of course. We have also done analysis in Kumasi, and we come up with about the same value. It varies from 6 to 9% per dry weight of fecal material. Why are we interested in lipids? Because, well, we want to make biodiesel from fecal sludge. Now, at this point, if I'm telling you, we are focused on 3 to 4% or 6 to 9% of total solids as lipids, we might as well shut this down and go home, because this is just too little to make this commercially viable and practical. And so then the question was, yes, we are interested in biodiesel because it's sitting at a far higher value than some of the other end products. But then the question is, can we do something else? Do we have to rely only upon this 3, 4, 6%, or can we come up with a system where we can just not only focus on the inherent lipids, but take just about any organics and convert them to lipids, convert them to fat? And that's really the focus of my talk today, essentially taking any organics and making fat, making lipids from those organics. And so let's take another look at feces. This has been presented quite a bit in this conference. And we all know what fecal material contains. The numbers might be slightly different, but the picture is about the same. And so we are not focused on this aspect, the water content. We are focused on this. And so again, like I said, if you just look at the fat content which is inherent in feces, it's a very small value, but it's basically just a small fraction. What we are trying to do is look beyond just what is inherently present and look at everything else which is present and make lipids and therefore make biodiesel from this as well. So that's what I'll focus on. And ultimately, we want to develop a platform. We want to develop a process, and we are well on our way there, which is agnostic to the waste stream. So again, surely fecal sludge feces can be a feedstock, but then we would like to open this to sewage sludge, to animal waste, to agricultural organics. You give us some organics and we'll get you biodiesel. That's what we would like to do. And so this is where we are very, very grateful to the Bill and Melinda Gates Foundation. They took this idea. They didn't laugh at us, at least not in front, and they were kind enough to support this. And well, I'm happy to say that we have some rather positive results now. It's taken some time. So this is, again, just to reiterate, where we want to start. And then the question is, can we make biodiesel? And so the answer is yes, of course. And the way we've done this is we are able to channel all these different organics, which contain all sorts of different things: carbon, nitrogen, phosphorus, microbial quality, inorganics, and so on. We're able to channel this through a fermentation and anaerobic fermentation-based platform, which can take in a variety of sources. And the anaerobic fermentation platforms produce precursors of biodiesel, and then we go to biodiesel. I think there was somebody who raised the issue of scale. That's very helpful in even guiding the conversation here. So for our process, anaerobic fermentation has been done at full scale for a long time. One of the first projects I worked on at full scale was actually anaerobic fermentation of sewage sludge and food waste. And we were, again, the point was we're making precursors of biodiesel even then. This was 13 years ago. At that point, the end point was not biodiesel, it was something else. Okay, so maybe before we go to anaerobic fermentation, let's take just half a step back and see what anaerobic digestion is. Essentially, anaerobic digestion is the sequential cascade conversion of complex organic materials down to simpler organic materials like acetic acid, and then also gases like CO2 and hydrogen, and ultimately leading to methane formation. And if you look at this cascade, the last step is really the rate limiting step under most cases, and typically under a given range of temperatures. When we design anaerobic digesters for different organic carbon sources, we typically tend to design these digesters at a hydraulic residence time of about 10 days or even higher. And again, this is the generality. This is the general trend. This is anaerobic digestion. Now, if you look at anaerobic fermentation, what we are doing, the only thing we are doing is we are taking out that last step of methanogenesis. And because all the other steps are relatively more rapid, we can get fermentation to acetic acid and some other short chain acids. Again, it depends on temperature, but even 1 to 2 days. So the advantage, one of the advantages is that when we rely on this fermentation-based platform, we are not looking at a retention time of 15 days or 10 days. We are looking at something which is quite small, quite short. And if you were in our presentation from yesterday that Justin made, fecal sludge comes in fermenting. It's active to come in, and so we don't even have to put in a fermenter. It's already coming in pre-fermented, and that's a huge advantage. And just to kind of make this point, I'm not saying throw out all the anaerobic digesters. What I'm trying to say here is we can incorporate fermentation into existing digestion systems. So that's also a good advantage. So this is our entire process train now. So we take organic waste, anaerobically ferment with certain precursors of biodiesel, volatile fatty acids, convert the volatile fatty acids to lipids, and then to biodiesel. I'm going to focus on this particular part of the overall process today. And so we have to be mindful of the fact, remember, we are talking about a spectrum of chemicals coming in, feedstocks coming in. And so what we really wanted to do was evaluate the capacity of this process to handle the diversity of feedstocks and ultimately still give us lipids. Our objective is to maximize lipid production. So we tested volatile fatty acids produced anaerobically from food waste by fermentation of food waste. This, talking in terms of scale, this is done in the lab. We also tried this in Kumasi. I'm not presenting those results, I'm presenting these lab results to start with. Then we also tested synthetic DFA, which we can purchase, and then as a reference compound, we tested glucose. We test a variety of feedstocks, we test different concentrations. Again, when we talk about waste streams, they don't only contain carbon, they contain nitrogen, phosphorus. So we also tested a whole range of carbon to nitrogen ratios, just to kind of simulate, at least partially, the range of substrates that we would like to put in and still get biodiesel feasible. And ultimately, our bottom line is to maximize the content of lipids that we are producing to maximize the biodiesel yield. And in terms of process engineering, we also looked at batch systems and continuous systems. Now again, just to reiterate, this is the back end of what we did in Kumasi at pilot scale. For us, pilot scale there was 120 cubic liters in terms of volumetric capacity. That's already done. This is more detailed research that we are now describing. And so let's go straight to the results. So what I'm plotting here is as follows. I'm plotting the concentration or the content of essentially the concentration of cells that we produced when we fed them with when we fed this process with volatile fatty acids. So we take volatile fatty acids and produce cells of yeast. So this is like brewing. This is similar to brewing beer. We are using yeast to make lipids. And then this is the lipid concentration, the dark blue bars. And then finally, these gray bars are the percentage of the yeast cells which are showing up as lipids. So this is the amount of accumulated lipids inside the cell. And here on the x-axis, I'm showing you essentially a representation of the different feedstocks that they put into the system. And just to kind of summarize this, what we are showing is that when nitrogen is present in excess, we get a certain signature. This is the amount of cells produced, this is the amount of lipids produced. This is the percentage of the cell that is comprised of lipids. Now, when we look at waste streams which are lower in nitrogen, lower in proteins, for instance, then what we actually see is that the lipid content increases. And these could be streams which are rich in carbon. These could be brewery waste, which was a big deal in Kumasi where we were running a pilot study. So if you have brewery waste, we are probably looking at something like this. Essentially, the positive aspect of brewery waste could be that is that we accumulate more lipids. And thereafter it kind of levels off. These are based on statistics, so these are actually, they are not just imaginary things, these are actually based on analysis. So this is only part of the picture, because here we are saying that with nitrogen limitation, we are able to increase the amount of lipid accumulation inside our biological system. And just to kind of highlight this, the numbers I'm showing you here, which are on these axes, 30% accumulated as dry cell weight. This is the highest ever reported for this biological system fed with volatile fatty acids. So this is, if you look at literature, this is the highest ever reported. Now, this is only part of the picture, how much the cell is accumulating in terms of lipids. We are also mindful of the fact how fast these cells are accumulating, because how much governs how much biodiesel we can make, how fast is how big our system is. And so this table essentially shows us these rates of cell growth. And just for a moment, if we just take, just understand what this means, essentially the higher the number, the higher the cells are growing, the smaller the reactor. That's what this means. So we see with increasing degrees of nitrogen limitation, so let's say this is only a carbon-based feed, we are getting a lot of lipid accumulation, but the cells are growing slow because they're limited for protein, they're limited for nitrogen. So then the question is, from the engineering perspective, how do we design this, right? So if you look at the data that I present here, this ratio seems to be somewhat optimal, and this was somewhat close to what we were getting in the field. So it kind of works out. So we're not compromising at all on how fast, and we are also getting good lipid accumulation. But at the end of the day, even if we get something which is very rich in nitrogen, the cells are growing fast, and the process is still working. And so essentially, this process can handle a variety of feedstocks. These are two aspects: how much biodiesel can we produce, how big our reactor is. The final part of the picture is what are we producing? What are the lipids? What are the lipids that these organisms are accumulating? Because if they accumulate the wrong lipids, we are not going to make biodiesel, which is going to be useful. We don't want the biodiesel to congeal at lower temperatures. And if you just take a look at the type of fat, type of oil that these organisms are making. Let's not go into the details, just take a look at these signatures. If you take a look at these signatures for different carbon to nitrogen, for anaerobic food waste fermentation, for glucose as the reference, essentially what we are making is very similar to palmitic, oleic, and linoleic acid. Basically what we are doing is we are producing soybean oil and jatropha oil. But we are not growing soy, we are not growing jatropha, we are making this from food waste. And we are making also this from fecal sludge. So that's the point here. So now we are completely disrupting that link between agricultural crops for biofuel. We are making this from waste organics, not agricultural crops. And for this, we also want to have some fun while doing this, and I know this is probably not equally exciting to all of you here. We did go one step further, and we really wanted to understand what we are dealing with here in terms of biological systems. So now we have actually the genome of the organism that we are using. And again, this is only for part of the audience, but we now know what drives this organism, so again, we can squeeze more. This is very minimal optimization that we are doing. Finally, what is the bottom line? Can we do? Yes, we can do this. What does this all mean? So we went through some analysis, and maybe we can discuss during the presentation, during the panel discussion. We are basically sitting without any optimization about 70 cents per liter of biodiesel. This is assuming that we actually have to do fermentation. If you looked at our presentation yesterday, we don't have to do fermentation. The fecal sludge comes in pre-fermented, this goes out. And here we are using the lowest possible number that we got in our system, so the number actually is far more favorable. The point is you can directly put fermented fecal sludge into our system, get the acids out, and make liquids. And again, the point is we're not competing with the biodiesel industry, with the food, with the chemical industry. We are using this to sustain the enterprise of sanitation. Finally, I'm not going to touch upon this. We are also looking at, as is somebody else in this audience I know, we're looking at the prospect of using BFA for not only chemical production, biodiesel production, but also disinfection. And if there are questions, we can take it on. So to summarize, this is our system. We have a platform which can take in not only fecal sludge, but mixtures of organics, and take these mixtures to lipids, to biodiesel, and lipids can also channel into commodity chemicals, so that this is quite promising. And we are not relying just on the inherent lipid content, which is quite limited. We can make our own lipids from just about everything. And again, we are disrupting the link. We don't have to grow food crops to make biodiesel anymore. We can do this from just about any organic. And I'll stop here.
Thanks, Ari. Very interesting presentation. I think it shows how innovative research can be on fecal sludge, which is absolutely exciting. I would like to give the floor for 2 questions maximum.
Hi, Sally Brown from University of Washington. We did something similar, except we used anaerobic digestion for energy recovery and then applied biosolids through canola and extracted biodiesel and cattle feed. In fact, the city of Portland is doing this with their biosolids. My question for you is, with you have the lipids in the cells. How do you extract the lipids from the cells, and how difficult is that process? And also, what is your end residual product like?
Yeah, I didn't show these. Essentially, that's just a schematic. It depends where we are. You know, in the U.S. in developed settings, we can use solvents. I mean, here we use the BD process, which is quite commonly used. In Kumasi, Ghana, where we were doing this, it's expensive. And it's not just the expense. We were on the upside, middle of nowhere, nothing. There's nothing. And so we were using petroleum ether, which also contains a fraction of the solvents that we want. And so Martin was here, we were able to get comparable extraction efficiencies and also of the right compounds, so that was quite favorable. What do you do with the residuals? This is the link I made. You're not throwing away digestion at all. Take all this and put it into your digestion. And so it's not biodiesel and or methane, it's not biodiesel chemicals or methane. This is on top of methane. We're not sacrificing that. We're not sacrificing methanogenesis. So what we are saying is split the overall anaerobic conversion into acidogenesis and methanogenesis. And that's the way to go about it.
Frank Phillips from Carolina State University. So the understanding is that in the lab, the influent VFA composition was 6:1 to 3, I think it's like, right?
Yeah.
So how variable is the process based on that? Or do you have to control the acidic, propionate, butyric acid ratios?
No, so the 6:1 to 3 was in a couple of places. So it was in the fermented food waste organics. So this is a real stream, not artificial, real food waste. We also have the composition from the fermenters in Ghana. It was somewhat similar, and I think it's a combination. We know it's a combination of the way you run the fermenter, so the hydraulic residence time, the temperature, of course, and to an extent, the carbon to nitrogen to phosphorus ratio of what is coming in, but also the carbon speciation of what is coming in. So in that sense, food waste and human fecal sludge turned out to be somewhat similar in terms of their impact on the volatile fatty acid speciation. I can tell you right now, you put in brewery waste, you're going to end up with butyric acid, but that's okay. That's not a challenge.
Okay, I think in the matter of time we have to stop with the question. We have a panel discussion later, so hopefully we can ask some more. Thanks again. Please another round of applause for Carlo. So with this, I would like to introduce our second valued speaker. We have already heard a lot about connection to Ghana and Columbia University and Kumasi. So we've got Arto Fangi Martin, who's not from Cape Town, but from the University of Science and Technology in Ghana, and he's a PhD candidate, and at the moment he is at the Columbia University. So this is the connection, and I'm happy to welcome him here.
Thank you, Lars. Great. I'm excited to be here. So I'm Fangi Martin, and as you mentioned, I'm from Ghana. And I'm doing part of my research at Columbia University. I'm looking at step-feed anaerobic fermentation, and novel alternatives for fecal slide processing. The co-authors are Professor Chandra, who just finished his presentation, Dr. who is not here. This happens to be part of the fecal sludge biodiesel project, and we've already had 2 presentations at this conference. So we looked at pilot scale operations and modeling yesterday by Justin Shi, and Professor Chandra just talked about liquid production. I'm looking at step feeding as part of this whole research. Now, generally, mixing happens to be a challenge in industry, and when we look at multi-phase digester systems, like what we had in Kumasi, having digesters in series, this happens to be a bigger challenge, because when you have a system where this is, you have it in a place where electricity provision is a challenge, you have to look at mixing as a whole. So generally what happens is that you have solid settling in the digesters when they are connected in series. So what we do to deal with this is that we step feed. Now the question is, what is step feeding? Step feeding basically is the stepwise introduction of influence in a treatment plant at several passes along its length. Now generally to step feed, what we do is that the conventional method. Okay, so conventionally what we do is that the influence is fed through the digesters and it's passed through from stage 1 to stage 6. But in step feeding, what we do is that you feed the system such that the influence is fed directly into the system so that you have each digester receiving the load. When this happens, what we do is that you are able to control solid distribution when you step feed. So generally, if you do not step feed, what happens is that solid settles. But in step feeding, you're able to control the solid distribution in the fermenters, in the digesters, and you enable substrate interaction with microbes. So this helps in controlling solid distribution when you step feed. Another benefit in step feeding is that it gives you turbulence. So I talked about the fact that mixing becomes a challenge. But when you step feed, what happens is that as you introduce the material stepwise into the digesters, turbulence is created, and that enables for mixing. In step feeding, one very important advantage that comes with step feeding is the ability to distribute load or toxins in the digesters. What do I mean by this? When you have a system where you have a high toxic load being fed into the system, such as ours, and it all goes into the first digester or the first fermenter, what happens is that you can actually have the system, the first digester crashing due to the high toxic load that is distributed to it. But when you have step feeding, you can distribute this high toxic load into the different fermenters so that the whole system is able to handle this properly. So our research question is in dealing with this whole system where we had settling in our digesters, we asked ourselves, can step feeding improve volatile fatty acid and butane yield? The second question we asked ourselves is, at what HRTs can this be achieved? Can step feeding improve volatile fatty acid and butane yield? So I want you to have this at the back of your mind as we go through this presentation. And secondly, at what HRTs can this be achieved? To do this, we moved from the pilot scale where we started, going back to the lab scale, the bench scale. So we already talked about the fact that we have done this work on the pilot scale. Now, to be able to do this in a more controlled way, we went back to the lab. So looking at this in the bench scale, the first question I will ask is that when you have a feed and you are working just in one stage fermenter and you are not step feeding, how do you do that? Very simple. You just load the material directly into the reactor or the fermenter. So when you are not step feeding, one shot, you load the material into the digester, into the fermenter. Now, when you have influent, the same influent, and you want to step feed in one fermenter, how do you do it? Can anyone give me a try? Can anyone give a try? If you are not step feeding, you load it directly into the fermenter. But if you want to step feed into only one fermenter, how do you go about it? You go about it with time. Now, what you do with time is that you can step feed with time in a cycle. So what we were doing with our system here is that we were step feeding the influence with time. So that we had a 3 8-hour cycle where the influence was introduced every 8 hours. So that is the way to achieve step feeding in one fermenter. And this is the system I work with in Colombia. And what we do is basically we have two, a step feed, a non-step feed fermenter, and a step feed fermenter. And like I said, for the non-step fermenter, you introduce the influence at one shot. But for the step feed fermenter, you introduce it in 3 cycles. You could also do 4 cycles or 5 cycles. But we look at 3 cycles where we fed the influence every 8 hours to achieve step feeding. And the parameters we monitored were COD, ammonia, nitrate, nitrite, VFA, total solid. And we looked at gas production as well, looking at the flow rate, and looking at methane and carbon dioxide. Now, I also want you to have this at the back of your mind. You've already seen this slide. Now, for the fermentation pathway, we realize that we have a 4-stage process. We have hydrolysis, acidogenesis, acetogenesis, and methanogenesis. Now, my work actually focuses on these 3. So I will be presenting results on hydrolysis. I have acidogenesis and acetogenesis combined because I'm looking at volatile fatty acid, and acetate happens to be in that stream. So I'm looking at it as part of the volatile fatty acid stream. And then finally, looking at methanogenesis. This first slide, actually, on the results, actually shows the conversion of total COD to soluble COD. Conversion of total COD to soluble COD. This actually is an expression of hydrolysis. This slide is an expression of hydrolysis. Now, what happens is that in looking at the step feed and non-step feed, we are also looking at HRT. So 2 things in mind, step feed and non-step feed reactor configurations. And then secondly, we are looking at hydraulic retention time. Step feed and non-step feed reactor configurations 1. Secondly, we are looking at hydraulic retention time. Now, when looking at this, first and foremost, what we realize is that hydrolysis increases with increasing HRT. So statistically, that is what we realize. At both 2-day and 4-day HRT, we have hydrolysis increasing. And then it levels off for both the step feed and the non-step feed reactor configurations. Secondly, this second slide is the conversion of total CO into volatile fatty acids. And this is what I talked about. So we moved from hydrolysis. Now we are looking at acidogenesis and acetogenesis. We've moved on from hydrolysis. Now we are looking at acidogenesis and acetogenesis. Now in looking at this, what we realize is that for the non-step feed system, what we realize is that acid production is statistically similar for all HRTs. For non-step feed reactor configurations, acid production is statistically similar for all HRTs. But when you look at the step feed reactor configuration, what happens is that it is similar at 2 and 4D HRT, but it decreases at 8D HRT. Another thing I want you to take home or look at carefully is that you look at this graph and you realize that these two 4D HRT and 8D HRT stand out because they look different. Now the reason why they look different is that this actually shows that at 4D HRT, so here I'm comparing the step feed, which is the blue, and the non-step feed, which is the red. Now at 4D HRT, what happens is that the step feed is slightly less, or is less than the non-step feed reactor configuration. At 8D HRT as well, we have a lower volatile fatty acid production in the step feed than in the non-step feed reactor configuration. Now, it's not just about the volatile fatty acid, the total volatile fatty acid that is produced. And also, we can also go beyond that and look at the specific acids that are produced. The specific acids that are produced. So here, I'm looking at volatile fatty acid speciations for the step feed again and non-step feed reactor systems and for the different HRTs. Now, if you look at this, what really stands out is that you realize that for all HRTs, acetates and butyrates are the dominant acids. For all HRTs, acetates and butyrates are the dominant acids. But then when you look at 4D HRT, you realize that succinates comes up highly here at 4D HRT for both the step feed and the non-step feed reactor configuration. Succinates. So the whole point is, if you are interested in succinates, you would go for 4D HRT, whether it's step feed or non-step feed reactor configuration. Now, another thing I want you to look at carefully is valerates. When you look at valeric acid, what you realize is that if you are looking at the step feed reactor configuration, you realize that it is decreasing with HRT. So at 2D HRT, valeric acid is higher at 2D HRT for the step feed, but reduces as the HRT progresses. Interestingly, it's the other way around for the non-step feed reactor configuration. So you look at the non-step feed reactor configuration, you realize that valeric acid is lowest at 2D HRT. So here also, if you are interested in valeric acid, then you will go for a shorter HRT, you go for the step feed reactor configuration. For a longer HRT, then you have to go for the non-step feed reactor configuration. This is what this means. Methane flow rates are similar across all HRCs for the non-step feed, but when you look at the step feed reactor configuration, what happens is that it increases with HRT. Conclusions. First and foremost, we've already talked about the fact that if you want to work with fecal sludge comes to us already pre-fermented. So if you want to work with fecal sludge, probably there is no need to ferment. But when you want to look at fecal sludge and food waste, it's already been talked about. And your goal is high-value chemicals leading to biofuels, as Professor Chandra talked about in biodiesel. Then you can do fermentation at 2 to 4D HRT. That is the point we are making, one point. Second important point, if you are looking at methane flow rate, biogas, then you can have an additional reactor. So here, I'm proposing one reactor for acid production, another reactor to optimize biogas production. And then thirdly, for the step feed and non-step feed reactor configurations, they are similar from a process point of view. But when you're looking at issues of mixing, you're looking at the issues of or the ability to distribute loads across reactor systems and ultimately to reduce costs. We will say that step feeding is a good alternate to the non-step feed reactor approach. And this is all that the research is about. Thank you. I would like to acknowledge Bill Emily, the Gates Foundation, And then the Kumasi Metropolitan Assembly, Mr. Tony Mensah is here, they gave us their land for this project.
Yeah, thanks a lot, Arno, for your representation. Very good timekeeping. I think it becomes very obvious how passionate he is about his research, and I'm happy to give 2 questions to the audience now.
Thank you for the great presentation. Just one simple question. How did you measure the hydraulic retention time?
So So hydraulic retention time, the whole reactor, the fermenter, is a 6-liter reactor. So in looking at 2,4, the HRT, we fed a specific period. On the pilots, we didn't do 2-4 days. So the pilots were feeding 5,000 liters a day. We talked about that yesterday. And our total volume was actually between 10 liters and 120.
So in the pilot scheme, there were in the pilot scheme system there were 6 reactors per train and 2 trains. Each reactor for about 1 truck of each reactor corresponded to a 2-day HR. And that's why we use the same increments for that as well.
So I had a quick question. So at these short HRTs, isn't hydrolysis becoming limiting?
I would not say so. You asked me if hydrolysis is limited. Is that a question?
Correct, because the whole premise is that you can produce, the rate limiting step is methanogenesis, you're shortening it, shortening all the HRTs, because then you can produce these DFAs, etc. But hydrolysis can be the rate limiting step as well. I was wondering if when you're shortening the HRT, is it not becoming the rate limiting step?
I wouldn't want to say so because we looked at different HRTs. So we looked at the whole range from 2, 4, 8 the HRT. So I wouldn't want to say so because we consider the whole stream.
In the interest of time again, I would like to close this one now and please give another applause to Arthur. So with this, I would like to introduce Santiago Septin-Stringel, who works for the PRG Pollution Research Group in Durban, South Africa. So you can see we're moving from Ghana down to Durban, and we'll have another South African presenter later. And he will tell us about the thermal properties of fecal sludge and inorganic nutrient content.
Dear public, I will present I want to present you this presentation, which is entitled Drying Characteristics, Thermal Properties, and Inorganic Analysis in fecal sludge Performance in the Pollution Circuit. So I will be to introduce you the context and the utility of drying in the sanitation world. This work was performed under the context of Revelatory Challenge, which is funded by the Linda and Melinda Gates Foundation, and its objectives is pattern removal and recovery of valuable resources from waste. The toilets should be not connected to the water, sewage and electricity grid. And the cost of the toilet has to be lower than 0.05 US dollars per user per day. Well, Pilatrines, we know, is one of the most spread toilet systems in the developing countries. Here we can see the single pit latrine, and here the improved version of the latrine. In Durban, in the Tukini municipality, we count around 30,000 VIP latrines. But when the VIP latrine is full, this can be a problem, especially in dense populated zones where we cannot bury the zone and pass to the next because of problems of space, lack of space. So it could be considered a waste, but as I said previously in Revelatory Challenge, we don't want it's a waste. We want it's a resource recovery, and with this we will see so fecal sludge as a resource where we can produce fertilizer, we can produce electricity, we can produce biogas. For this, fecal sludge has a very important position. Why? Because it can reduce the volume and mass of the waste, which by sure we are going to see in the bill by a decrease of the transport costs. It also lead to a pasteurization and kill all the pathogens, so the product will be safe. And so as safe, it can be used in agriculture. And it has a low moisture content and important organic contact, so it can have good characteristics, a good potential to be a biofuel. So the objectives of the present work are as following. I want to present you a kinetic study doing after experiments of drying in a convective ring. We are going to evaluate the agricultural potential of the dry fecal sludge, and he's used as a biofuel. Now, to achieve to these objectives, we do perform some experiments we are going to present it in the next session. Well, this is the convective drip, a scheme of the convective drip that we have used, where the dry air is humidified by water at controlled temperature. At the end, we have a saturated air at the temperature of the water. And it's going to be headed, it's going to be overhead, like this is not going to be anymore saturated, and it's going to be introduced in the drying chamber. Here we can see a photo of the drying chamber. Here we can see the humidifier. Here we can see he's hiding, but we can see the heater. And here this is the drying chamber with the balance connected to a computer where we are going to record the results. Here are the conditions. We are going to vary the airflow rate to 20, 40, 50 centimeters cubic per second. The temperature is going to be varied between 40, 60, 80 degrees Celsius. And the relative humidity is going to be between 5, 50, 25. The fecal sludge that we are using was collected during the emptying of VIP latrines in the peri-urban settlements with the Etiquini municipality. And he was stored in a cold room, and before the experiments, he was spread like a flattened layer of 7 millimeters thickness. Or, using a handheld extruder, we produce some pellets of variable size, 8 millimeters, 10 millimeters, and 40 millimeters. Both fecal sludge in a thin layer and pellets have a moisture content of 80%. Then, after drying the fecal sludge, as we can see here, we make chemical analysis by a spectrophotometer to see the soluble ammonia, phosphate, and nitrates, spectroscopy to see the phosphorus, potassium, calcium, and magnesium. And we also made some thermal analysis in the calorimeter pump to see the calorific value, and the TC analyzer to see the head capacity and thermal conductivity. Now I'm going to present the results of this study. But before, let's going to pass a little of that drying theory. So we can see that during drying, the moisture content decreased until a limit, which is called the equilibrium moisture content. And in the equilibrium moisture content means when the water and the solid and the air are in equilibrium. In a point of view kinetic, we have different sections. We have the BC section, which is called the typical constant rate period. In this period, the solid is saturated on moisture on its surface. And so drying occurs at this place, and is controlled by external transport. Then the drying rate drops, what we call in the first falling rate period, and this drop is caused because the surface is any more saturated. At the end, there is another drop in the drying rate because the drying occurs at the center of the solid because the surface is already dry. And by sure, this period is going to be controlled by internal transfers. And here, the passage between the transition between the constant rate period and the first rate falling period is what we call occurs in the critical moisture content. Well, so I want to present the results, and the results, I want to pass fast. In the results, we're going to begin with the effect of temperature, but we have to show the curves. It's going to be easy. Okay, well, we are right. Well, the effect of temperature. So here is the driving curves. We can see the evolution of the mass of the solid in an experiment normalized with respect to its initial mass for three different temperatures, 40 degrees, 60 degrees, 80 degrees Celsius, a constant flow rate and relative humidity for the thin layers. And we can see that when we increase the temperature, we are decreasing the drying time. Here we can see the values. And now we are going to see the same similar results, but this time we are going to vary the air humidity at constant flow rate, constant temperature for the flat thin layers. And also we can see that when we increase the drying time, we are decreasing when we increase the relative humidity, we are increasing the drying time also. And here we can see that the equilibrium moisture content is arrives when is completely for the different relative humidities is the sample is completely dry. There is no any more humidity. Then we are going to pass to introduce the effect of the airflow rate. So I vary three different flow rates. And here is the driving curves we have obtained, and we can see that the flow rate has only a slight increase, leads to a slight increase in the drying time. Here we can see that with respect to the other cases, to the temperature and the moisture content, the effect of the airflow rate, there is an effect, it's slight, but it's lower than the other parameters. And finally, we vary the sample. And we use three pellets of different size and the thin layer. First, if we compare the pellets size, we can see that logically, as we could expect, we have an increase in the drying time when we increase the size of the pellet. And then, if we compare the pellets with the thin layer, we can see that we achieve we have the same drying time between the 40 millimeters pellets and the thin layer. And this is because when we measure the characteristic length, which the characteristic length is defined as the ratio between the volume and the external surface of the particle, we can see that the characteristic length is similar and is equivalent to 3.5 millimeters. Well, the critical moisture content, I'm going to be very fast in this part, was measured from the drying curves, and we could see that there was no effect of temperature, moisture content, and air velocity, and only depends on the sample geometry. The critical moisture content was 60% for the flat thin layer, which is near the middle of the transformation, and the critical moisture content was 30% of the pellet. That means that the constant rate period occurs at 3/4 of the transformation. What is the implication of that? That you have longer constant rate periods for the pellet, which is positive for the process, because when the external transfer controls the process, it's easy for the engineers to have an influence with external transfers to influence the drying rate. Now, I'm going to introduce the chemical analysis. And here is the concentration of the potassium, phosphorus, magnesium, calcium at different, or pellets produced at different temperature. What we can see at first is that there is no effect of temperature, what we can see by the statistically. So we have around 40 grams phosphorus per kilogram, 20 grams of calcium per kilogram, and the concentration of magnesium and potassium is similar, is 5 grams per kilogram. This nutrient composition, if we compare it with the literature, is similar to the compost and manure. Now, talking about the soluble compounds, we can see that they are in very low concentration. We have less than 10 grams per kilogram of ammonia, less than 5 grams per kilogram of nitrates, and around 2 grams per kilogram of phosphates, which is only represent 5% of the total phosphorus. What means that the other part of the phosphorus has to be in the solid and not in the fraction, which can be very easy removal. What's the implication of that? That if we use it as a fertilizer, it will be a slow nutrient release fertilizer. Now, in the thermal analysis, we are going to begin to introduce the calorific value, and we can see for pellets produced at different temperature, there is no effect of temperature, and we find a calorific value of 30 megajoules per kilogram, which is a quite high calorific value if we compare it to that wood. It's similar to wood. It's similar to wood. It's 1/3 of coal and 1/3 of coal and natural gas. Well, for the head capacity, now if we see for the head capacity, we can see that for head capacity, we can see that there is no effect of temperature. The head capacity is around 1,450 joules per kilogram per degrees Kelvin, which is relatively low if we compare it to wood, diesel, coal, natural gas, but it's higher than coal. Now I'm going to finish to show you the thermal conductivity of pellets produced at different temperature, and we can see that there is no effect of temperature also for this property. It's a quite low thermal conductivity of 0.06 watts per meter per Kelvin. This is much lower than wood, than the other solid fuels like wood, diesel, or coal, but by sure it's higher than natural gas because the gas usually have very low thermal conductivity. Now I'm going to pass to the conclusion of all these experiments. The conclusions of the kinetic studies, we didn't find nothing extraordinary. We find what we have expected. That means that we increase the dryer rate by increasing temperature and gas velocity, and we decrease the dryer rate by decreasing the humidity and particle size. The most influent parameter was for much temperature, if we compare with the others. Under the explored conditions, in the most pessimist cases, we have 2 hours of drying, and the most positive size, in the most favorable condition, it was 1 hour of drying, like this for the processes, and we have to know this order of magnitude times. And the critical moisture content, which is an important variable, because as I repeat, is during the constant period is where the engineers can easily control the process. It depends on the geometry of the fecal sludge. Concerning the conclusions of the characteristics of the fecal sludge, we can see that first of all, the nutrient composition of dry fecal sludge is similar to manure and home compost, so we can say that it could be used like in agriculture, like a fertilizer or soil container. His content in phosphorus is considerable, not so high, so it's better to use it in local area or areas close to the seat. And as a fuel, has also good positive properties as a fuel, because it has a calorific value which is very close to that wood, and everybody will know that wood is very widely used nowadays, like for production of electricity and heat. He has very low capacity, which is positive because it can be heated faster. However, he has also a low thermal conductivity, which is an implication in the process, and that means that he has to be in particle size, in small particle size, in order to avoid limitations. This is Blessing Makonomika. He's a master's student who has made these experiments and has performed this analysis. Thank you for your attention. We would like to acknowledge the Bill and Melinda Gates Foundation for his funding, and here we have if you have more information, you can contact me at this email address. Thank you very much.
Thanks for your great presentation, Santiago. Particularly, I really enjoyed the visualizations, and sorry for the technical problems. We still have time for 2 questions.
Boris Gold from the Outstanding. Thanks for the excellent presentation. I'm very much interested in drawing of field research. Somehow your presentation cracked out at that point. Why is the critical moisture content so important? This critical point? Yeah. And why do you think it's different between the pellets and the thin layer?
Thank you very much for your question. To answer your first question, in fact, it's about the critical moisture content. It's very important because it's at first time is the maximum. Is when the maximum drying rate. So that means if the concentrate period is longer, the drying is going to be faster. And as is controlling only external transfers, that means that, for example, we can increase the temperature, we can increase the flow rate, increase the turbulence, to increase the transfer coefficients, and and we will increase the drying. However, if we are in the falling periods, that means that there are internal phenomena which is going to influence, and the problem of that is that everything is inside. It will depend on the properties of the solid porosity, and it's more difficult for it to influence these parameters, the internal diffusion. And the other is quite recent. This finding about this analysis was 2-3 weeks before the conference, so we have not time to see the difference. But it has to be of the phenomenology, but we have to go deeper in that research. Thank you.
Hello, my name is Oliver Ive from a company called Amantabantu Services. Clearly you're finding things you expect to find here, but did you do any further work looking at things like energy required to get the drying process done, so you can get some sort of energy balance required to put in what you need, the exothermal element of it. And the other thing is, when you go through further on and you raise your temperatures above 80 degrees, at what point do you start pyrolyzing and driving off the various volatiles, and what is that process? Are you going to take further into that as well?
Yes, for a moment we have not made energy input in the rig. So we have to include this for the future. This the energy that we need with the calculations. And respecting to the pyrolysis, we are very, very far from pyrolysis temperature, because the pyrolysis temperature really begins to 200 degrees Celsius, and with this apparatus, the maximum temperature we can reach is 100 degrees Celsius. Is it possible to pyrolyze at this temperature? The organic matter begins to pyrolyze at more than 150. It really begins that we can see the torrefaction begins in this area. But we are very far. So we can let there long time. We're going to maybe find as we find a very dry product, but with this apparatus, we don't have this risk.
I think, again, for the interest of time, I would like to introduce our next speaker. Thanks again, Santiago, for the great presentation. So our next speaker is also from South Africa. We're talking about David Still from PAD Pietermaritzburg. David is a civil engineer and he graduated at UCT, University of Cape Town in '84. He's been working in government and research between 1985 and 1993 in the Department of Water Affairs at the Council for Scientific and Industrial Research. Since '93, he's a researcher and independent consultant, and is working in FSM since 2007. And as we all know, he's organized FSM 1 and 2, so I'm happy to have him here as a presenter this time. I'm sure he's also happy about it, so let's listen to his research.
Okay, all you chemical engineers out there, time to kick back and have some fun. One of the questions is, when the pit is full, if we have to empty it, what do we do with the sludge? And earlier this morning we've been hearing about some of these options like anaerobic digestion, better kinds of anaerobic digestion, pelletization and so on. We're hearing about pyrolysis. Elsewhere, the last 2 days you might have heard about black salt and lime stabilization, all these things. All great things, and in their context, where the economics are right, make a lot of sense. However, I would appeal to everybody working in people sludge management not to lose sight of the wood for the tree, should we say, and not to forget what I would call the default option, which is burial on site. In many cases, it doesn't make economic sense to go beyond the site. If people are living on decent-sized plots, if they're miles from anywhere where we process the sludge, where you don't have these dense urban situations. So where space is not a problem, there needs to be a very good reason to move the sludge from the site where it's generated. Once you start transporting sludge, your risks escalate and your costs. So, a lot of people will tell you, oh no, the reason we're doing this complicated research, the reason we want this $1 million grant is because people sludge contaminates the groundwater. But how do we know that? Do we know that? And when might it be true and when not? And I challenge you to do research on that, to read the original research, to do your own investigation. You will not find a lot of work done in the world ever scientifically that really establishes. I mean, I'm not saying it doesn't happen, it does, but really constrained and very, it's not like, wow, you know, it's just, you have a pit between suddenly a well 100 meters away, it can't be used. Another thing is, okay, well, if the groundwater is shallow, if your pit is intersecting the groundwater, well, then you're definitely polluting the groundwater. Again, how do you know that? Where's the hydraulic load? What do we know about the ability of sand in soil to filter out pathogens and to absorb and reduce nutrients? Now, those of you, hopefully not all chemical engineers, some of you might have done environmental engineering. Environmental engineering 101, you learn about the slow sand filter. In a slow sand filter, number one, it's saturated, okay, so it's flooded. Number two, you've got porous medium. You select a porous medium. Number three, you get a log 4 reduction in your pathogens in the first few centimeters. Okay, that's how slow sand filter works. So why doesn't that happen around pit between there? So you've got far less hydraulic loading, you've got less porosity. And what about resource recovery? Of course, that's very important. If you've got a large stream of waste in a big city, you should be doing something with it. But if you're going to spend $2 to recover $1 worth of resources, then why are you doing it? And I have heard presentations on web and wonderful ideas, and I ask the presenter, have you done the economics of this? No, we first want to see if it works. If it works, then we'll look at the economics. You've kind of got to do the two in parallel. Inspiration for a lot of the work I've done on burial sludge is reading about terra preta soils, which soil scientists get very excited about. This is a photograph from National Geographic. In the Amazon, we've got very high rainfall. The soils get leached of a lot of their goodness. And the indigenous people who lived there for hundreds or thousands of years have been burying their organic waste in the soil to improve its fertility, with amazing effects in terms of depth of topsoil, fertility of soil. Soil is the most complex ecosystem in nature. Soil microorganisms comprise fungi, bacteria, algae, protozoa, and number in the range of several million per gram of fertile soil. They break down organic matter and cycle nutrients. It's very complex biology, which I barely understand. For me, as a civil engineer, it's a black box, and I'm just scared I put something into it and I look at what comes out of it. And it's available to use for free, so why don't you use it? Okay, our very first trial was just a quick and dirty look-see where we emptied some pit latrines near where I live. We were interested in how people would react to emptying them, how they would react to using it with trees, and we did some controls. And it was just a small study. And this was one of our first responses. The tree on the end was buried on a mixture of soil and fecal sludge, and it was bigger, greener, more fruit. That one had some commercial fertilizer for some reason, didn't do well, and this one we just planted in the ground. Okay, so that was a quick indicator that looks promising. We then did some trials, controlled trials with concrete towers. We had a master student working on it, did a good job of actually doing everything scientifically, and he had control towers where he planted the tree and he used liquid chemical fertilizer, and then he had experimental towers where he put in a core of sludge, planted the tree above the core of sludge, and he got like 300% better growth on the tree planted over the sludge. Now you won't get that over 10 years, you get a more rapid response in the early months. But there was a very definite, marked difference. And then one of the questions said, will the roots get into the sludge, or will they avoid the sludge? Is the sludge not too different to soil? Well, after 6 months, after he broke it all up and had a look, there you go, the sand has fallen away. That sludge, you can tell it's sludge because of the trash, and you can see the roots are growing into it. And that's fairly new sludge, it's not old sludge. So then we did another trial. Those of you who might have gone to FSM1 a few years ago might have come to this spot. We buried over 1,000 tons of fecal sludge here in less than 1 year. It's an old oxidation pond. We were interested in tree growth, in groundwater contamination. So there were pits being emptied in the area. There were trenches of fecal sludge put in there. There's my learned colleague, Mr. Chris Buckley, who many of you will know, modelling our groundwater purging looking. Okay, so we looked at a number of groundwater things. We had 5 background wells between the sludge and the river, and we monitored that for a couple of years, and we never picked up anything at all. We monitored the tree growth rate, and got some indications that the trees were happy over the sludge, although the controls were not well designed, so that wasn't very conclusive. And then a few years later, we were periodically augering up the sludge to analyze pathogens and to look at the characteristics. And after a while, my guys started to battle to find the sludge. And we put 1,000 tons of sludge there. They'd come back and they said they couldn't find the sludge. Finally, we dug great big pits so that we knew we were in the sludge, but you could see the trash. And after a few years, you can barely tell the difference between the sludge and the soil. Trash helps, but it's changed so much. It's very like soil. It's a bit more organic, a bit more spongy, but very like soil. We looked at the hardiest pathogens, ascaris, to see how long they survived, and we were pretty happy that after 2 or 3 years there was nothing left, starting with pretty high levels, because Durban is an area with high ascaris. So we were happy to conclude that after 3 years your ascaris would be dead, but there's no real reason why you'd be digging it up anyway. Okay. Then we did another trial. We wanted to get better controls on the effects of the sludge on the tree growth, but we hadn't designed that very well. So we did something with commercial forestry using sewage sludge. Near Maritzburg, it was a bit wet with raining. We dug trenches, we put the sludge in. We had a number of plots, some with sludge, different amounts of sludge, some without. And after 4 years, what we're seeing there is about 50% more biomass in the trees on the plots with the sludge. Possibly possibly a decreasing effect. So I don't know if that 50% is going to be sustained right through the end of the growth cycle, but definitely a positive response. But we're not seeing like 200%, 300%, which you sometimes read about. Of course, it might depend on what trees you're planting in the soil and things like that. It was very nice. What's going on? Okay, that's fine. If I leave it. Okay. Okay. While we're waiting for that slide to come up, we also monitored it heavily, groundwater, all sorts of instrumentation around the sludge, and then background monitoring holes below the sludge, working with my colleagues at UKZN, Simon Lorenz and Co. And just advanced. You can see at the bottom of the plot the two red dots, those are background holes going on. Okay, and what the guys found in the first summer, I think, we had about 1 to 2 milligrams, not milligrams, yeah, 1 to 2 milligrams of nitrate per litre more in the downstream borehole. Okay, so there was a slight change, but relative to safety levels and all that, not very significant. And then if we get the phosphorus one up just now, on the phosphorus, they didn't pick up any change. That was the first year. The second year, you couldn't pick up any difference at all. There was no trace of any impact of nutrients. So that's the phosphate. We couldn't pick anything up, right? That's stopped it. So then we did the people I was working with on the groundwater monitoring could still not really produce a mass balance of what happens with nitrogen and the phosphate that we put in the ground. And we worried that maybe there'd been such a rapid response that a whole lot of it had leached off in the first 6 months before we really got the monitoring going properly. So then currently we're doing a very controlled leachate monitoring trial where we bury sludge in 1 meter plots. Leave it there that one. Well, actually go back 1 meter. Yeah. And some of these 1 meter plots have got what they call pan lysimeters. That's well, there it is. Okay, it's a steel tray, and that's got some gravel and geofabric, and then we've got soil. So that tray is about 1/2 meter below the sludge, and we've got instrumentation around the sludge as well, so we're able to measure every little bit of leachate that comes with that sludge. And right there, they're burying sludge, well controlled. We've got about 30 plots, and let's see, go, yeah. And they even made it rain. We measured it so far over about 10 months. We had about 800-900 millimeters of rain, and this stuff there. And what we found, we're not looking at patterns here. This experiment, I'm interested in the nitrogen and phosphate. What happens to it? If you look at the bottom there, after 10 months, after nearly a meter of rainfall, nitrogen 0.16% average, median 0.1% of the nitrogen has got through to the leachate pan. Okay? And the phosphorus is nothing. So we're not having a major impact on the groundwater here at all. Okay. So where does all the nitrogen go? Again, it's pretty complex biology, but if you read about it, with all this complex biota in the soil, there's quite a lot of cycling. And obviously some of the nitrogen stays there and takes years to break down, but some through nitrification, denitrification, it actually cycles back into the atmosphere. And phosphorus absorbs the clay molecules. So phosphorus I don't think actually goes anywhere. So if you are interested in doing something where you can plant trees over decades, the phosphorus that you put there is going to benefit the soil for decades. So, concluding now, the environmental impact of sludge burial in the ground, sludge decomposes by natural biological processes. After a few years, is barely distinguishable from surrounding soil. After 3 years, even the hardiest pathogens die off. And despite high loading rates, no significant impact on groundwater has been observed in our trials. And I'd urge everybody who's interested, please go and do your own trials. I'd love other people So conclusions. Disposal on site into a nearby pit or a trench is the simplest, cheapest, and most practical option. Plant a tree or trees over the sludge to gain some advantage from the nutrients in the sludge. And if you don't want or can't bury the sludge, composting it for local use is probably the next simplest, best option. Again, answering nature to do your work. Thank you.
Thanks again for your presentation, David. Sorry again for the technical problems. Hopefully we're going to get that solved on the next one. So we have time for questions. 2 more for David, and then we can also invite the other speakers here.
My first question is, how much did you buy a hectare, for example, how many tons? Or how deep?
What we would advocate is about 200-300 millimeters, but not over the whole hectare. We were trying it between the trees. In that last one where we looked at those 0%, 0.1%, we were looking at directly about, well, some of them were 250 millimeters and some were half a meter of sludge. So we're looking at what we got below half a meter of sludge or 250 millimeters of sludge.
Would you agree on average, if you agree, plots like where you 20, 30, half a meter, free area, and then you do it again, maybe on average 10 centimeter on an area in the forest?
Yes, it wouldn't average over 10 centimeters.
This is about 1,000 tonne per hectare.
Yeah.
Sludge contains 5% of nitrogen. You apply 50 tonne of nitrogen. So this is a huge nitrogen load in the yard. I'm not sure it's all science. So this can be very dangerous, and you need to do the mass balance here. Even if you don't find any detail in the first year, this is the time for.
Yeah, but the I believe a lot of nitrogen is actually cycling back into the atmosphere. Because we're not finding it in Egypt.
You need a lot of carbon to get denitrification. You need anaerobic situation, which you won't have in these situations. So unless you measure the nitrogen coming out of the system as anaerobics or nitrogen, then I'm not sure what.
Okay.
I wonder, in many countries you wouldn't get resource consent for this kind of application because of the nitrogen.
Look, I don't think it's got a lot of application in large scale. The application is really in more rural areas where you are literally taking the sludge out of this pit and you're putting it over there. And so then your loading is actually quite low because you've got maybe a ton and it's over a few thousand square meters. If you're doing it at large scale, it's just not going to happen because of transport costs, because of regulations. That kind of thing tends to happen more with the wastewater treatment industry and the more regulated conditions.
Hi, Dave Robbins. Thanks very much for the great presentation. One question. I'm not sure what the depth to your groundwater was in your trials, but if you had groundwater at like 1 or 2 meters, can you still do direct burial, do you think, and achieve the same kind of results? Thanks.
If the groundwater was, I wouldn't advocate burying into the groundwater. I think those are the kinds of situations where one should be looking at composting and all sorts of other applications. Our groundwater was below the pits that we were digging. But just a comment to supplement what I've said. The risk of pathogens burying sludge in the ground is a small risk, acknowledged. But compare that to the risk of not having sanitation, compared to the risk of having sanitation that you don't use. We heard yesterday or the day before about very high quality communal sanitation in Haiti, which is only used 50% of the time because it's communal sanitation. Compared to the risk of emptying practices which are poorly regulated and controlled and shit goes everywhere, compared to the risk of sewers which are poorly managed, which is very common in the city where I live. The median fecal coliforms in the surface water, based on 1,000 data points a year for the last 3 years, the median fecal coliforms is 10,000 per 100 milliliters. That's in the surface water. And we're worrying about a couple of bacteria a couple of meters from a pit.
My question, thank you very much for the presentation. My question is about the amount of rainfall that is received in the area? How much is received in the area?
The areas where I'm working, our mean rainfall is 800 millimeters to a meter. So moderate, more than some places, certainly less than many places. But we've even been simulating rainfall with those tests where we've been adding rainfall.
Okay, thanks again, Dave, for the presentation, answering the questions. One round of applause for Dave, please. So let's begin to do that sometime, and I would like to invite all four speakers again to come to the stage. And if there's any more questions, maybe some cross-cutting issues, we had discussed this very detailed technology options. We have some other options that could be possible, especially context-specific options. We can take considerations. So, yeah.
Thank you. My name is Mesa. I'm from Masika. My question goes to the first two presenters, Professor Chandram and then Kato. I want to shift the discussion from the academic point of view into the real world. We are seeking to solve real problems, real life problems. This concept of conversion of ficus line to biodiesel, some other works have already been done, and then looking at those and what you have done and the results. Of course, we've not reached the end of the tunnel yet, but the question I want to pose is, do we have light at the end of the tunnel? And how bright is the light?
Yes, thank you. I would say that surely there is light at the end of the tunnel. For the process of converting fecal sludge to biodiesel, as Professor Chandra said earlier, one of the challenges is drying. And we have seen a presentation here which was amazing actually dealing with drying. So in my point of view, if that energy component can be taken off, I think that for the other aspects of converting the volatile fatty acid produced to lipids and producing biodiesel, that we've already done. Our little bit that we have to do is still with the drying issue, and we can easily move on from there.
So you know, you were quite familiar with this project. It's taken us 3 years and some detours along the way to get to where we are. I think so. So we know we did produce biodiesel at scale on site as well, using the inherent lipids, which needed drying. That's what Martin's talking about. And I think it's also, in terms of light at the end of the tunnel, it's also always useful to keep in mind or keep thinking about alternate endpoints. Ultimately, I think we are all in the same objective to more sustainably manage fecal sludge or other waste outputs to the environment. Biodiesel is part of the ecosystem solution. There probably are plenty of others more applicable in some other places, some which are more applicable in some other places. And that's also, so we have to keep in mind other possibilities, but also where and what they will cover. Sorry, can I take 1 minute to answer one question that was posed? I perhaps just ran through this. In terms of the most favorable BFA for lipid production, it's acetate at the end of the day, and so we can get to acetate. We know how to get to acetate.
Well, I mean, it's not just substrate; it's also the microorganism, right? It's going to push it. But we can talk about that.
Yeah.
But actually, I have a comment for Atto and then a question for Dave. And I think that looking through the step feed, non-step feed. I mean, sitting here, I just realized you're talking really about the CSTR versus the PFR, right? At the end of the day, it's a completely stirred tank reactor versus the flood flow reactor. And the more you actually do the step feeding in smaller increments, the closer you are to a CSTR. So in many ways, I guess the point that I'm trying to make is, we know a lot about CSTR versus PFR, whether it's anaerobic or other situations. So I think there's some theory there that we can apply. So that's common.
I'm going to jump on this. Sure. It's not CSTR at all. It's step feed versus non-step feed. And we can talk about it. This is not CSTR at all. It's not.
No, but if you, well, we can talk about it.
Yeah.
Okay. So I guess the comment there is there's a lot of theory in other fields, including just traditional environmental engineering that we can apply. Right? So there's some that we don't have to reinvent everything. And I guess for Dave, what about pore flush toilets? So with pore flush toilets, right? When you open them up after they're dry, they're really like soil, and they've decreased in volume. But obviously there's a lot of water involved. And then again, in a situation where it's an urban situation where you have, pit toilets left and right and very high concentrations. You can imagine the water fields that basically are very close together and very saturated conditions maybe. What's your take on that in terms of transport of nutrients and pathogens?
My colleagues Simon, Lorenz, and Bruce Wickham, in their study on movement of contamination of groundwater from pit latrines and pore flush, they looked at a number of pore flush sites, some which have high groundwater tables where they're basically flooded, or not right up to the surface, but to near the surface, and they haven't picked up plumes beyond about, I think, 8-9 meters. That's kind of the zone influence. The zone influence is more, but not hugely so. And then where it's not flooded, you get good drainage from the leach pit, and it's easy the contents are not very different to a pit, especially if they've stood for a few years. They're actually a lot easier to work with. There was a question earlier to me about the nitrogen loading. There's one thing on the nitrogen loading we remember is that the nitrogen content of species which have been sitting in the pit for 5 years is much lower than fresh species. And also there is a high carbon content, so that also mitigates the FP1.
So we have managed to stay on time for the coffee break, which will give you a chance to ask many more questions to our presenters. And thanks again for the excellent timekeeping, which is why we can end now. I would like to give another round of applause to all for the presenters.